Hello everyone, welcome to Galvanometer and Ammeter. Now let's start with galvanometer. Well, it is a device used to detect current. So it just checks if there is the presence of current or not. Now here we have to learn about the principle of galvanometer, which is just a few sentences. So before that, have you ever been to a lab and grabbed a galvanometer and just shaked it silently or gently, not too hard? Well, if you shake the galvanometer, you can see that the needle just deflects on its own. Even though it's in your hand and let's say the wires are not connected, anything is not connected to it, and you just shake it, but even still the needle shakes. That means that the needle is connected to something that is suspended somewhere so that it's able to move, right? So here, for galvanometer, it works on the principle of, well, a coil suspended in a magnetic field. And when current is passed through it, well, this coil actually deflects. That means it experiences a torque which is equals to npia cos theta. We will learn about this derivation in the future. Don't worry about that for now. So that means if a current is passed, then the coil will get deflect, and if a needle is attached to it or linked to it, then the needle also will get deflect as well. Now here the current passed through the galvanometer in a circuit is known, well, the max deflection that it can occur, the current can occur, Ig, is called full scale deflection current. That means this is the utmost deflection that the galvanometer can have, right? Because it starts from 0 right here. These are the max points. So it is called full scale deflection current. And if a current is, well, more than the full scale deflection, what happens? Well, the galvanometer can get damaged. It does not read the current reading, right? So we have to use another device. This device is known as shunt. So shunt is a, well, very low resistance device which is connected in parallel to the galvanometer, so that, well, let's say a large current, let's say I is coming across it, then it will take, well, let's say current I dash, so that current Ig only flows through the galvanometer. So here I dash using the junction rule is simply I minus Ig. So here we can adjust the value of shunt so that we get the full scale deflection for the galvanometer. And here, to increase the range of the galvanometer so that it can, well, read more, well, be more sensitive and read current of higher value, we can decrease the shunt value so that it takes more of the current, and so that, well, only full scale deflection goes through the galvanometer. Now here, when a shunt is connected in parallel to galvanometer, it is known as ammeter. And here, the parallel combination of galvanometer and shunt is known as ammeter. And here this ammeter is always connected in series to the ammeter. And here we can also find out the value of shunt or the resistance of shunt. Because here what we have is IgG, I minus IgS. And we know in parallel combination the voltage remains the same. So that means IgG, which is IR, is equals to I minus IgS. So therefore we get S equals to Ig by I minus Ig into G. And here this G is the resistance of the galvanometer. And here I forgot to mention the galvanometer also has low resistance, so that, well, it can get more current, right? And as I talked earlier, the ideal, well, if you decrease the value of S, the resistance, that means more and more current can go through galvanometer, thus increasing the galvanometer's range. That means the ideal resistance of the shunt goes to 0. right? Because if it goes to 0, that means galvanometer can read high amounts of current. Now here, as I talked earlier, this ammeter is always connected in series to the circuit. There are four reasons. First, because it is a very low resistance device. Second, if it in series, the ammeter here reads its own reading, right? It reads its own current reading. But in series, the current is same. The same current flows throughout the series. So that means ammeter also reads the current of the cell, the driver cell, battery, or the circuit. And here, if it was connected in parallel, it would be the opposite case. Since it would read its own current, and in parallel, the current is not same, that means it only reads its own current, but not of the circuit. And also, if it was connected in, let's say parallel, like this, here the ammeter would, since it's a very low resistance device, and in parallel, it will get, more and more less, because here there's a rule for series and parallel. If something is connected in series, the resistance will be greater than the greatest, and here in the parallel it will be lower than the lowest, and here its resistance will be so low that high amount of current will flow through it. High meaning that excess current will flow through it, more than what we want for this ammeter. And here we can also calculate the value of ammeter, which is A, let's say RA is equals to, since these are in parallel, this is actually 1 by RA equals to 1 by S plus 1 by G. Now using some quick maths, the resistance of the ammeter is RA is equals to, SG by S plus G. Now this is all for galvanometer and ammeter for today. If you learned something new, please like and subscribe. Thank you.